let's welcome our next speaker, Cécile from France. Her talk is about moire material progressing there. Yeah.
Thank you. Yeah, thank you. All right. Hi, everyone. So thank you very much. And thanks a lot to the organizers for setting up this beautiful school. And I would like to thank Yonglong especially for inviting me and not giving up on inviting me when I said no the first time. And, you know, I always had very good reasons. So finally I could make it and I'm really glad. All right. So my lectures are going to be focusing on moire materials and what we can say from the point of view of theory. Is it here? No, it's not changing the... Oh, but I would be very near it. No, I don't think that's the problem. That works? Yes. Okay, perfect. Okay, so I think probably a lot of you have heard about moire materials and know that these are two-dimensional materials that are obtained by stacking very thin layers of materials. So let's go right in and say what these are. So let's start with the building blocks. And so the building block is going to be a really thin, mostly atomically thin layer of a material. And a very good example is graphene. So graphene is this single layer of carbon atoms that forms a hexagonal lattice. And if you look at its band structure, it has this very interesting property of having Dirac cones that will come at each of the K and K prime points, so at each of the corners of the Brownian zone. So you have relativistic electrons, the semi-metal. So another very popular choice in terms of two-dimensional materials, especially when you want to build moire materials, are transition metal that chalcogenides, or TMD, and I will probably keep saying TMD in the rest of the talk. So they're not one atom thick, as you can see if you look at this view. They're more like 3 atoms thick because they're made out of one transitional metal atom with 2 chalcogen atoms in purple. But this still gives you a hexagonal structure, and these are layered materials that you can exfoliate, so it's also possible to obtain a monolayer. And in some cases, they will be semiconductors. That's what I will consider later. And so this is the band structure for one example. And so that's quite different from graphene. So you see that we have quite a lot of very different starting points, and there are many TMD materials. So that also gives you a lot of options. So now moire heterostructure. So the idea is going to be to stack at least 2 of these layers with some lattice mismatch. And the lattice mismatch is going to give you some interference pattern in real space that is called the moire pattern. So here is graphene again. So this time 2 layers of graphene twisted slightly, so slightly misaligned, otherwise known as twisted bilayer graphene, will give you a moire pattern in real space. So here is a sketch of what it gives you. And you see that you have a really small length scale associated with the lattice constant of graphene and a really large length scale. So this is the moire superlattice. Right, and this is something that can be seen experimentally in STM experiments. And just for a little bit of publicity, I took some images from a colleague from my own university in France, in Grenoble, where you see both the graphene lattice and the much larger moire superlattice. So twist angle, starting with twice the same material and slightly mislining it. Twist angle is one way you can obtain a moire. It's not the only one. You can also use two different materials with a different lattice constant. So common example would be graphene on hexagonal boron nitride. And it's an interface that's very common because it's common to encapsulate graphene in hexagonal boron nitride. So this will give you a moire because those two materials have a lattice constant that has a mismatch by about 10%. And you can also use TMDs, and you can do, for example, hetero bilayers of TMD. So one layer of one TMD material, another layer of another TMD material, and I will also, for the same reason, give you a moire. Continuing with examples, you can do twice the same TMD and have a twist angle, or you could do more than two layers, and I will give you a moire with even more different properties. So, for example, 3 layers of graphene, or 4 in twisted bilayer graphene, where each bilayer itself is aligned, but then there's a twist between the two bilayers. So this is all to say that there are many, many different types of moire materials, and in principle, this is really a playground where each of those is going to have different properties. So exploring those, you can hope to find many different phenomena. So here, what we are mostly interested in is going to be when correlations are especially enhanced. And I think this is one of the most exciting things about moire materials is that they bring the possibility of having really strong correlation effects because of the possibility of having flat bands. And so before going really into some more precise things, some more concrete things, and even the possibility of flat bands, I wanted to give a pretty general argument relating to having at least a reduced bandwidth when you have a moire pattern with a long wavelength. So for this, I'm just going to do a sketch of a band structure, and I'm just going to do it in 1D because it's much easier to draw this way. So this is energy, and in the horizontal, this is the wave vector k. And because I had graphene in mind, I kept a linear dispersion. So I'm starting from a decoupled model where blue is one layer, let's say top layer, red is bottom layer. Okay, so this is decoupled. And you have some crossings, some band crossings between blue and red. And of course, these crossings are not protected by anything. So as soon as you include any coupling between the two layers, interlayer tunneling, there's going to be some level repulsion, and you're going to open a gap at the crossing between these two layers. And additionally, because you have this moire pattern, there's going to be an effect from the moire potential in terms of a Brillouin zone folding. So in real space, you now have a much larger lattice constant, meaning that now your Brillouin zone in momentum space is much smaller. So everything that happens at the boundary of the Brillouin zone is going to become folded back onto itself. So, right, so let's say that this is the boundary of my first Brillouin zone. So everything that happens on the right side of this, I actually have to report back on that side, and same thing with the blue here that I should put back on this side. And again, this gives me more crossings that are where there's going to be level repulsion. So at the end of the day, I'm creating many, many bands with some gaps. Maybe they are a bit small, but some gaps. And overall, if I'm focusing on the band that's around 0 energy, this band is going to have a much smaller bandwidth than the original bandwidth that we started from in the single layer material. Right. So this is one very good motivation to include a moire in two-dimensional systems. And there's going to be some more motivation as well. So it's actually going to be an extremely tunable platform. So one thing that we don't have in many strongly correlated materials, which are very often bulk materials, thinking of cuprates, for example, is the possibility of tuning the electronic density without changing the material, so without actually doing some chemical doping. Here, because these are 2D materials, we're going to be able to have a gate on top and one below the system, allowing you to change the chemical potential as much as you want. I think possibly another advantage is the theoretical modeling, is that you're going to, maybe it's not going to easily give you what the strongly correlated phases are. Definitely it's not going to give you but you have a weakly interacting starting point that can put you in the right direction. So what I mean by that is the single layer is weakly interacting, and so you know its band structure relatively well, either from first principles or from experiments. And so you can use that to build some relatively simple models, and those can give you an idea of the band structure of a moire material and point to you where you should be looking at and have a rough idea of where the band structure should be relatively flat. And I think an extremely important example of this is magic angles in twisted barrier graphene, which basically were predicted using a continuum model, the Bistrisser-McDonald model, and which predicted that around 1.1 degree you would have extremely flat bands, and that's what you had to look at. And indeed, when looking there were some strongly correlated phenomena. Right, so this was my general introduction and motivation. So let me give you the outline for these 2 lectures. So today I will be focusing on single particle properties only. So we are going to be talking about general models, band structure resulting from it, flat bands, and also a bit about topology. Because some of these bands are going to be topological. And in the really wide field of moire materials, I chose to focus on magic angle twisted barrier graphene and twisted homobilayer TMDs. And you have to make a choice, and this one is motivated by the fact that I think from the experimental point of view, those are materials where there are lots of important experiments and new phenomena. They've been important historically as well. Many new things have been seen in these materials. And they're also going to set up the stage for lecture 2, tomorrow, where I'll be talking about strong interactions in these materials. So we have a flat band, so once we turn on interactions. And more specifically, I'll be focusing on correlated insulator and on Chern insulators, so both integer and fractional. So this is going to have us talk about quantum hole ferromagnetism in the absence with or without a magnetic field, and fractional Chern insulators, which are the lattice equivalent of the fractional quantum hole effect in the absence of a magnetic field. Yeah, but for today, let's start with single particle properties, and let's start with twisted barrier graphene. And so again, this is graphene, the single layer. And so this is a hexagonal lattice, and you have 2 inequivalent sites, which are the A and B sites. So if you look at the band structure, as I was saying earlier, this is a semi-metal, and at all the points of all the corners of the Boolean zone, there are Dirac cones. So you have this linear dispersion, and there are actually 2 inequivalent corners of the Boolean zone, K and K prime. So this is going to give you 2 different valleys. And you also have a spin degeneracy because electrons carry a spin. Now, what about twisted barrier graphene? So we put two of those on top of one another and rotate with a really small twist angle. So you now have this large superlattice. And now in the K view for this, so the Brilliant zone view is that you're going to have a mini or moire Brilliant zone. So this would be the Brilliant zone of graphene. I have two of those that are slightly rotated by the twist angle. And this gives me the new corners of the moire Brilliant zone. Okay, so what about band structure? Okay, there's some slight mismatch there. Anyway, so I'm going to more or less this is the introductory argument that I was telling you earlier, is that you're going to have a folding of the Brilliant zone onto the mini Brilliant zone. And at the same time, you're also going to have interlayer tunneling that gives you level repulsion. So you end up with many bands, but you want to focus on what is around charge neutrality. And so this is a picture of what happens from Yuan Kao's paper, where you see that as you decrease the twist angle, you bring the Dirac cones closer together, and the level repulsion is such that the bands flatten. And at some point, there's a magic angle condition where the Fermi velocity vanishes. And so this is the magic angle of 1.1 degree. So before going into the model, I would like to focus a little bit on some general arguments still of symmetry and topology. So I have my Brilliant zone again, same as before. And I just want to repeat the degrees of freedom that I have and which ones are conserved. So I have spin, and this is an SU2 degree of freedom because I'm not considering any spin orbit coupling. So SU2 spin. And I'm also considering a conservation of the valley quantum number. Essentially, when you have such a large twist angle, the two valleys are really far apart in momentum space, so inter-valley scattering is strongly suppressed. So you can neglect it as a first approximation, meaning that the number of electrons in each valley is a good quantum number. Now, something very important to notice at this stage regarding topology is that if I'm looking at one valley, we have Dirac cones, and they are preserved by the same symmetry that protects them in graphene, meaning the product C2T. So T is time reversal symmetry, and C2, so this is in-plane rotation symmetry, so in-plane inversion. So we have the same Dirac cones as graphene protected by the same symmetry, but they have a very different property, which is that for two corners of the mini Brilliant zone, the Dirac cones have the same chirality. So they have the same chirality throughout this valley, and then the opposite chirality throughout this other valley. So what does it mean to talk about chirality for these Dirac cones? I can see it in the way that I write down an effective Hamiltonian near the K point. I can also say that my Berry phase is winding in opposite directions for the red and for the blue. So if I'm going around the Dirac cone, the Berry phase is going to wind this way or wind that way, and this is what's represented with these little circles here. And so this is a very fundamental property, and it's going to have some importance later on, especially if we want to gap out those Dirac cones. And this is going to have a very strong importance for the ensuing Chern numbers. So I mentioned before the Bistructure-McDonald model. This is a very paradigmatic model now, I think, in moire materials, but probably in condensed matter in general. So this is a continuum model for twisted barrier graphene. So yeah, no, before I say this, I also should say that, okay, so why do you need a continuum model? I think it's quite obvious that once you have such a long superlattice constant, you have so many atoms within one wire unit cell. If you keep a tight binding approach, this is going to have so many degrees of freedom, and maybe some of those are not so important to consider. So at low energy, it's nice to have an approximation that gets rid of some of those degrees of freedom while capturing the essential physics of the flat band. And this is what the continuum model does. So again, starting from the single layer, we can write down the Hamiltonian of graphene in K space, like so. Here, psi K is a two-dimensional spinor where you have a number for the wave function of what's located on side A and what's located on side B. And then H of K is a 2x2 matrix written in terms of the Pauli matrices. And here we can take the approximation that we are around the K point, so we can linearize the Hamiltonian by just writing it like this. And so it's enough to write down the Hamiltonian for twisted barrier graphene, it's enough to write down its Hamiltonian just for K, because K, the other value is completely decoupled. So K prime is completely decoupled. And it's just going to be the time reversal partner of this value. So let's comment on the terms in the Hamiltonian. So the first line is just the decoupled layers, right? So I have the original graphene Hamiltonian for the top layer and the graphene Hamiltonian for the bottom layer, where I've added some indices theta over 2 to say that I did a rotation. So I rotate theta over 2 on top and minus theta over 2 in the bottom. And then I have an intra-layer term that's going to couple the two layers of graphene. And this is the term that carries the moire potential. So here, it's going to, because it's associated with the moire potential, it's going to couple, in the Boolean zone, it's going to couple K with K plus G, where G are moire reciprocal lattice vectors. And so this term is just the intra-layer tunneling. So the intra-layer tunneling is local. And so you have places on the moire lattice where you have A on top of A. So you're going to tunnel from A to A. And this is with this value, with WAA. And in other places, you're going to tunnel from A to B or B to A, and with WAB amplitudes. And so this gives you this matrix here. And in general, electrons prefer to be tunneling from A to B. This is the preferred stacking of graphene layers. So this leads to relaxation effects. And it means that typically we have a ratio of WAA to WAB that's less than 1 and roughly around 0.8. Right, so this model was, as I mentioned before, was used to predict the emergence of magic angles where you had flat bands, but these flat bands were found with a 0 Fermi velocity. I think there was an addition to this work that came much later on by Tarnopolsky and collaborators of finding what was the true origin of the magic angles. And to understand that, they found a limiting case of the Bistricher-McDonald model with WAA equals to 0, which is now called the Carroll model of twisted barrier graphene. So what happens when you turn off this tunneling between A to A, this interlayer tunneling between A to A? What happens is that the model acquires a chiral symmetry. So meaning that now the spectrum is going to have an exact E goes to minus E symmetry. And doing so, they found that at magic angles, the band is perfectly flat. So here is the band structure that they found. And there's actually a very profound reason why this band becomes very flat. It has to do with the mathematical structure of the wave function in the flat bands in the chiral limit, which now those wave functions now really resemble Landau level wave functions. So there's something to do with holomorphicity. I won't get into the detail of that, but there's something very important about whenever, in the chiral limit with at magic angle, whenever you have a zero mode, then you can show that you can build zero mode for any k as long as you have one for one single point in the Boolean zone. So if you can do that, then your band is perfectly flat. And another piece of insight that came with this work was a periodicity of all magic angles. So it was already known that there are several magic angles. The 1.1 degree is the first one. The only thing is that experimentally, the other ones are really hard to access because they are even smaller than 1.1 degree. Right. So let's talk about topology now. So we've talked a lot about energetics, and earlier I mentioned that the Dirac cones were protected by C2T symmetry. And you can actually break C2T symmetry by imposing a staggered mass. So let's say plus m for A sublattice and minus m for the B sublattice. And that's going to open a gap. And interestingly, this is something that's experimentally relevant because aligning the graphene layer with the substrate of hexagonal boron nitride actually gives you effectively this staggered mass. And in the continuum model, so in the Bistritzer-McDonald model, this is a really simple addition. You just add an extra m sigma z term in one of the layers, the one that is aligned with the substrate, and nothing else changes. And what's the result for topology? So now you open a gap, so you can calculate the Chern number of each band. And interestingly, now each of the bands of these flat bands have a Chern number, a non-zero Chern number, -1 or +1. So let me detail a little bit what is shown here. You can focus on the left because going from left to right is just a spin conjugation, and nothing changes when you change spin. But in one valley, you are going to have Chern -1 for one band and Chern 1 for the other band. And because it's the other valley is its time reversal partner, now the Chern numbers are going to be opposite. So Chern 1 below and Chern -1 on top. So if I make a sketch of the flat band and the different bands that we have, including all their degeneracies, I have a conduction band and a valence band with a substrate-induced gap, which if may or may not be present. If there's no alignment, this gap would reduce to 0. And in total, I have 8 bands, which are either Chern 1 or Chern -1. And this is where I think it links nicely with what Joel was presenting in the previous lecture, is that this is really due to this peculiar structure of the Dirac nodes in graphene, because if you just had one layer of graphene, adding a staggered mass would open a trivial gap. So both bands would have Chern 0, right? In the Haldane model, if you just add a staggered mass, you don't get a Chern insulator or topological insulator. But here you do, and this is really because this chirality here is the same on all corners of the mini-Boolean zone. This is really what allows it. If you want a maybe simplified way of thinking about it, you're adding up the chiralities. So either they're the same, and then you can go to something non-trivial, or they're opposite, and then the net is 0. Right, so that's pretty much what I wanted to say about twisted barrier graphene. So we can now move on to twisted TMDs. And so just a quick reminder of the single layer TMD. So again, it's going to be yeah, shouldn't switch. This is a hexagonal lattice with 2 different types of atoms. We are going to consider semiconductors. And more specifically, we consider cases where the maximum of the balance band is located at the K point. So K and K prime. And this is the case in particular for WSE2 and MOTE2. And one really key property of TMDs is the fact that they spin valley locking. So it's due to having a strong spin-orbit coupling in this material. So when you focus around K, you have one spin polarization only. And if you focus on K prime, you have the other spin polarization. And we are actually really going to care mostly about what happens around K. This is, in the perspective of thinking of a twisted barrier. So this is going to be the same process as what happened for TBG. So if you want to build, for example, a continuum model, what you really care about is what happens around the K point, because this is what's going to give you the flat band. So this is what we need to model. So we can make an approximation for the single layer of simply a parabolic band, like so, with an effective mass for the electrons in the band, representing what happens right here. Right, so another continuum model was built for twisted TMDs, also by McDonald and collaborators. This is a schematic picture of where it comes from. So you're considering your parabolic bands, and there's going to be some interlayer tunneling. So this is K, and then independently, you're going to consider K prime. Again, because exact same argument as twisted barrier graphene, you have a conservation of the valley charge. So you consider the 2 valleys completely independently. So this is the continuum model for twisted homobilayer TMD. And so you see, so now it's much reduced in terms of dimension compared to the twisted barrier one. And the first reason is that we start, in the single layer, we start from a single band instead of starting from 2 bands. So this reduces everything by 2. And also the spin valley locking. So that's another factor of 2. Instead of being almost degenerates 8 times in TBG, now you will have a band that's almost degenerates 2 times in twisted TMD. Right, so this is for the top layer where you recognize the term, the parabolic bands of the TMD. Same thing below. And then you have these 4 terms that come from the moire potential. The main difference from TBG here is the addition of an intra-layer moire potential, which is essentially negligible in TBG, but has a really crucial importance in TMDs. Right, and those are, again, written in terms of the moire reciprocal lattice vectors. So what about energetics? So there are some parameters in this continuum model. They are these okay, they are the parameters essentially of the moire potential. So intralayer, amplitude of the moire intralayer plus some phase parameter that says how it modulates in space, as well as the strengths of the interlayer moire potential. And all those parameters are determined through DFT calculations typically. So here is a calculation in twisted WSE2, which shows you that you can, for some angles, have an almost flat band and others have a really nicely flat band, which as you go to larger angles will become more dispersive. And I mentioned earlier that you had to come up with a value for these parameters. It's not an easy thing to do, and I think it comes with a lot of finesse, and there's been a lot of different results that are not, I wouldn't say they're necessarily completely contradictory, but to obtain enough precision on where, which angle is the band the flattest and etc., it becomes a bit tricky. And so this is an example for twisted MOT2 of results without relaxation and with relaxation. So we see that it plays a really big role. And I think the reason this calculation was made was after strongly correlated phases were observed in this material. I think it came as a surprise that they were observed at a relatively large twist angle, larger than what was expected earlier. And so theorists had to come up with an explanation. And so including more different parameters in the ab initio calculation was a way to reconcile this finding with the theory. But just to say that there's a lot of sensitivity to different things, and especially relaxation, meaning that your lattice is not perfectly rigid. Once you stack the two layers, there's actually some adjustments, and these are harder to take into account at the ab initio level. Okay, so finally, topology. In twisted barriers of TMDs. So I think an interesting fact is that in twisted TMD, you start from bands that are completely trivial. And even we made some simplification in modeling these bands, or at least what happens around the K points, modeling that with a parabolic band. So you see that you cannot get more trivial than this. So here, the possibility of topology is going to come not from the underlying single layer, but really from the coupling, from the moire potential. And what Wu and McDonald and collaborator found is that the moire potential actually has a really, or the interlayer tunneling potential has a really interesting structure that makes it possible to hybridize the bands enough to make them topological. And more specifically, if you build this vector that's made out of the different moire potential, so the interlayer and intralayer part, so it's a vector that you can that they plotted in the Brilliant zone. You can show that it has a non-trivial texture in the moire unit cell. So it actually has a skyrmion texture. One way to think about it is that this vector, so which is just this first vector just normalized in terms of the block sphere. If you go if you go through the entire moire unit cell, this vector will cover the whole block sphere. So this is what it means to have a skyrmion number. And this is what makes it possible to have a churn number in the bands. This actually corresponds, there were some numbers on the previous slide showing what was the topology of these bands, but yeah, so in many cases they are topological, but not in all cases. I think also that's an important point to make, that there are some regimes where the bands are topological and others where they are not. Yes. No, this is really, so it has, I think it has nothing to do with the, wait, I need to think this is really correct. This is really about the moire potential itself. So the way that moire potential, and winds in the, well, yeah, the different components of the moire potential, how they wind in the veneers. Okay, no, I think it has more to do with how its real path sometimes is. Yeah, okay, that's not going to answer what you're saying. Does it help if I go back to the expression of delta T?
I guess I'm thinking of that. Like, I understand you have much less bands in graphene, but this kind of fermion texture is not there.
No, so in graphene you only have this delta T. You don't have the delta plus and delta minus. So you only have the xy term of that vector, not the z term. So you cannot go around the whole sphere. Yeah. Yeah.
Get a sense of which angles.
No, so I think what they showed in this paper is that sometimes you have a skyrmion sector and a skyrmion, and yet the band is trivial. So it just offers you the possibility of having a topological band. And yeah, I was thinking about it and trying to make the analogy with two band models where where the Hamiltonian vector, you can also say that its skyrmion number is the Chern number when you have a two-band model, right? So like h of k, hx, hy is z. And in that case, it's a pure one-to-one correspondence. It's really strict. Here, this is not a two-band model, first of all. This is many bands. And second of all, this is a skyrmion in real space, whereas this other argument is a skyrmion in momentum space. So I think it tells you that you can have a Chern number, but it doesn't prove that you have one. I think you need to do the calculation, the entire calculation, to show that you have one.
There's some sense.
Yeah. Yes, probably. There's probably a limit where you can see that there's no way that you can do the full skyrmion. So maybe in some limiting case, then you no longer have the skyrmion, and then the band is trivial. Yes. Yeah. And this actually already brings me to the end of this first lecture, where we can summarize the different points that we talked about. So long wavelengths moire patterns generally reduce the bandwidth, but the relationship between twist angle and bandwidth is highly non-universal and model dependent. So this is just a tendency. And then when you look at what happens at small twist angle, you can find very interesting phenomena. Specifically in TBG, there are exact fact bands which are given in the Carroll limit. And this Carroll limit model is helping explaining it with a mathematical structure of wave function that resembles lambda levels. In twisted TMD, there are nearly flat bands as well. And yeah, maybe a point to make about twisted TMDs is that the fact that you're starting from a parabolic band rather than some linearly dispersive band is maybe more forgiving if you want to do like a twisted barrier, because you're starting from something that's already a little bit flat. And so maybe there's like a slightly larger range of angles where you can find correlation effects. And Yeah, the other very important message is that flat bands in wire materials can be topological through very different mechanisms. So we saw the case of twisted barrier graphene, where what happened was that you have Dirac cones with the same chirality within one Brillouin zone, so that adding a trivial staggered mass was enough to create topological bands. Whereas in twisted TMDs, this was really the topology was created by the skyrmion texture of the layer pseudospin. And so tomorrow we'll talk more about the consequence of these flat bands and topology when we add interactions, focusing on channel insulators and fractional channel insulators. Yeah, so now I'll be very happy to take any questions.
Hi, thanks for the talk. I was just wondering, sort of maybe a more general question. When you showed at the very beginning, like you had your Brillouin zone for the monolayer, and then on the corners, you have like the smaller you have the smaller Brillouin zones for the moire. Do I think of those as like living in like the same momentum space, or should I mentally have those like separated, and should I be allowed to think of them as like actually inhabiting like the corners of the Brillouin zone, or is that just more for like fiction and there's no physical intuition there?
You mean the two different valleys? Are they?
Yeah, like when you have the big hexagon.
Yeah, no, I know it's okay. So maybe it will take a while to go back. Yeah, this one, for example.
Yeah, exactly.
So those are really the same. I mean, if you're talking the single layer in relation with the twisted bar layer, yeah, these are the same. And then if you're talking those two in relation with one another, yes, you can think of them as decoupled because there's no scattering between them.
But can I think of like the big hexagon and the smaller hexagons as like existing in the same sort of K space, or should I think of them as sort of like living in completely separate spaces, as I guess what I'm.
So I guess in your mind, you're going to want to think about like what's, you have a notion of a first Brillouin zone.
Yeah.
And so this is your first Brillouin zone, and this is your first Brillouin zone for graphene. But like otherwise, physically, I'm not sure which kind of connection you can make between the two, right? Like as soon as you have the twisted bar layer, the graphene by itself is something different.
Okay, thank you.
Yeah, I'm not really sure how to better answer your question.
Any other questions?
Thanks for the nice talk. I have like two naive question. One is like in presence of this Carmion type texture, what happens to the flat band which was appearing from this folded Brillouin, because that's a real space texture. So does this affect the folded Brillouin zone structure because of the real space variation?
Yeah, so this so we're thinking of a skyrmion of essentially the term that hybridizes those initial layers. So this is the term that actually produces the flat band. And then if you want to know where the flat band is, I don't really know of anything else other than doing the calculation.
Okay, thank you. And another thing is, since it's a real space Carmion, then the momentum space, so how does like in some kind of transport signature, or how the two will manifest differently? Like, does it have different transport behavior than twisted bilayer graphene or the twisted thing?
So definitely, because one has a gap and the other does not. And then you have to think about which filling you're thinking of. So far I didn't really talk about transport signature, because if, even though I have topology, okay, so I'm thinking, if I have a churn number, so I should have some sort of quantized Hall effect maybe. But to know that I need to include interactions because I have Chern number, but I have another band in the other valley with the opposite Chern number. So if I don't include interactions, I never have any Hall effect, right? But with interactions, we'll see that at integer filling, for example, interactions will fully polarize the system into one of these bands, which leads to a quantized Hall effect.
Okay. Thank you.
Any questions still?
Hi, thank you very much for that nice pedagogical. So yeah, I have a question. So you mentioned TBG and you mentioned twisted TMDs as well. And I'm curious because there are some systems, for example, where you have a large lattice mismatch, like at TMDs and graphene, or bilayer graphene and TMDs that are very interesting experimentally. And in some of those systems, you can have, there are, commensurate moire patterns that occur at very large twist angles, like 38 degrees, that have moire patterns that are order of magnitude or more smaller than in TBG. So the continuum approximations that we're used to seeing in, these twisted homobilayers really fail very badly. So I'm curious on a practical, practically, are there, tractable approaches to, studying those sort of, those large twist angle moires outside of continuum?
Yeah, it's a very good question. I don't know. I just haven't studied those and I haven't, maybe it sounds like you know more about this topic than I do.
Just curious, because I saw some experiments, you mentioned ARPAs, and I remember seeing some experiments, ARPAs at large twist angle, and they see, mini bands and things like that.
Yeah. I mean, okay, so I talked about the continuum model, but I should say that some people still do real space approaches, right? So these exist, these are still doable. It's not because we like to simplify things. I think it's more the reason to use continuum models is, yes, it's practical, but also it's a kind of a reductionist approach where you want to take out as many of the unnecessary parameters as possible so that you understand the system better. But I think tight binding approaches are still very much like people do them, and they are definitely useful in this type of case.
Thank you.
Any more questions?
So maybe a bit of a pragmatic question. From the band structure of the twisted MOTE2 versus twisted WSE2, is there some systematic difference, or it's sort of the difference that's in the details?
I mean, from what I've seen, I feel like it's really hard to tell from far away. Like we now know with experimental data that they are very different, but I don't know. I think FCIs were predicted in WSE2 before being predicted in MOTE2, and then they were observed in the other one. So it's one of those things where the simpler theories fail to make good predictions, and you have to include more realistic terms, and it becomes like the differences energetically and also in terms of geometrics are so subtle. I mean, one really small change in parameters will make things change quite a lot. That it's really hard to tell.
Thanks.
Any more questions? Okay.
I can ask maybe one quick follow-up to that. So you told us about sort of two qualitatively different, kinds of flat bands, one from the graphene with direct cones and one from these quadratic bands, both of which give interesting topological bands. Are there other kind of possibilities, like maybe not even specific materials of like, here's a third, maybe qualitatively thing, or do people feel like that space is pretty saturated?
Yeah. So in terms of something that would be qualitatively very different, I think you'd have twisted trilayer graphene, where you have flat bands plus Dirac cones.
So like for the like twisted TMDs, right? You do this like quadratic expansion around the K point, and then you like couple those two layers.
Yeah.
How do you recover like periodicity of that Brillouin zone? Or is this just like a purely like low energy kind of
Yeah, it's a low energy picture, and then you couple those, and your periodicity is given by the moire lattice vector. So you impose it in a sense. You impose the periodicity of the moire.
I think it's hard